helpful to you to have to think through it? Rather, I mean, it's different when I'm up here. I just do it, right? I'm just like doing it. I'm leading exactly where you need to go. Hopefully you having to sit there and think about it was useful. Okay, look at this one. Order might matter. This is a slightly different problem because what I've done is I've given you a double integral. It's already set up for you, right? So you could say to me, hey, you know what? This is the volume, right? This is the volume below this surface right here. This, if you were to graph this surface, it's the volume below that, right? But this is your domain, right? The domain comes from this. So what I'm going to do is if I tried to integrate that right now, I would run into a major problem. Do y'all see this? What's the antiderivative sine of y squared with respect to y? No, not happening today. You can't do integration by parts. Let's see what Wolfram says, okay? I'm going to put in here just what's the antiderivative of sine of y squared with respect to y. Let's just see what Wolfram says. Yeah, probably. Nope, it gives me square root of pi over 2 times capital S of the square root of 2 over pi y. What the hell's capital S? Capital S is the Frenzel S integral, which we never even study ever in Cal 2. So this basically is Wolfram saying it's beyond what you know what to do with, okay? You don't have a way of doing this. Now you could use power series, you could use series, but we should be able to hopefully do this, right? Okay, but we can't do it, right? So what we're going to do is we're going to take a look at the region right now, okay? Let's look at what we have for the domain. The domain for us, right, is the set of points x and y such that, can you tell me the restrictions?
Y is 1 greater than x less than 1.
Okay, so y is bigger than or equal to x, less than or equal to 1. What about x?
Greater than 0.
Between 0 and 1, right? Do y'all agree with that? That's our domain, right? That's our domain. What does that look like on the ground? X between 0 and 1. And your y's are between x and 1. Do y'all know what x looks like? What is it? It's this, right? That's y equals x. And what does y equals 1 look like? Horizontal line, like this. This is D, isn't it? Do y'all agree that picture of D right there is what that domain? So take a step back. What I'm saying to you here is that by just knowing the limits of integration and the, with respect to what variable, by knowing that, I should be able to come up with a definition of the domain, and then I should be able to sketch it, right? I should be able to sketch it. Right now, we can't solve this integral because we don't know how to do this with respect to y, right? What I'm going to do is I'm going to switch it now. I'm going to change my d. Instead of a type 1, I'm going to change it to a type 2. And the reason I can do that is because this is also a type 2. My y's are between what two things? If I look at this, this was type 1. But if I look at it as a type 2, my y is between 0 and 1, right? My y is between 0 and 1, and now my x's are between what two things? 0 and what's this function? You have to solve it for x, right? So x equals y. So your x is between 0 and what? Y. Now, why is this useful? Do y'all see it? Are y'all seeing ahead why this is useful? To switch it? Let's see. Let's see why this is worth us doing. what does this double integral look like if I do it as a type 2? We go 0 to 1 here. That's our restriction on y, right? And then here we go 0 to y, right? Then we do sine of y squared. Then what? This is the key. Then what? Dx dy. And that's critical because if I integrate this with respect to x now, this is just a constant. And so what's the antiderivative of that with respect to x? Let's work through this. Let's work through this. Any questions on why, like how I switch from a type 1 to a type 2? Everyone see it in the picture? Type 1 is, okay, x is between 0 and 1, and the y is between x and 1. But we looked at it the other way and said y is between 0 and 1, and x is between 0 and y. By doing it that way, it allows us to switch the order of integration, which allows us to attack that integral. So we've got integral 0 to 1. Okay, antiderivative of that with respect to x, just sine y squared times x, right? Or you could put the x in front. From what? X equals 0 to x equals y, and then dy. And now this becomes integral 0 to 1. Okay, I'm going to plug in for x, right? Yeah, this second one's going to go to 0. This one's just going to go away because when we plug in 0 for x there, it's gone. When we plug in y for x, we get this, and I'm putting it in front. Y sine y squared, right? And do you see that this one we can do? Because that's a basic u sub. The derivative of y squared is 2y. You're off by a constant. So we can actually handle that integral, right? So our next step would be integral 0 to 1. Let's just write this one more time. Y sine y squared dy. The antiderivative of that. Without showing the work, can I not show the work? Negative 1/2 cosine of y squared is the antiderivative evaluated 0, y equals 0 to y equals 1. Right, because I can just make a basic u sub. U is y squared. I'm off by the constant. Du is 2y dy. I have a y dy, so just scale it by 1/2. That y being here made all the difference in the world, didn't it? And the only way that showed up is by me converting it from type 1 to type 2. So that's why this says here, order might matter, right? Order might matter. The way you order the order of your integration can have a huge impact on your ability to integrate something. All right, so I'm going to stop there. Any other additional questions on that?
I have one question.
Yes.
At one point in our academic career, will we ever face that integral? What was it, Barrett?
Oh, Frenzel integral? Probably never.
Okay, cool.
Yeah, unless you're a math major, maybe. But the thing is, we have these functions that allow us to get answers to integrals. Okay, so let me back up. If you were to take all the functions that exist and put them into a big pot, right? And then close your eyes and reach in there and grab a function. The probability that you could actually integrate it by hand is essentially 0. Like most things, there's not a nice way to integrate them. I know we spend all that time in Cal 2 learning all these techniques of integration. But at the end of the day, in the real world, you're most likely not going to be able to integrate the functions that you're dealing with. So we have to have techniques to deal with those. And that's where series come into play, right? Series allow us to rewrite functions as these infinite series of powers of x, and then we can integrate that all day long. The drawback to that is that there's going to be error in our answers. There's always going to be some error. So, but we can make that error as small as we want, which is okay, because in the real world we can only manufacture things to a certain tolerance anyway. So if our error is still within some window that we can work with, then it's okay, right? So these Frenzel integrals, and you'll see these other things like the error function. These are just functions that allow us to calculate the answer within some margin of error. So that's what it was doing. It was giving you a margin of error, all right?
Okay.
I don't know if that answers what you're asking, but good question. The bigger, I think, question is when you type this into, when you're an engineer and you have to do an integral, because you do have to do integration. In the real world, there's meaning to these things. Do you trust the computer that gave you that answer, right? So who knows the math behind the algorithm that got you that answer, right? That's the bigger thing. Do we just trust the answer? Do we feel good about it? All right. So some more things about double integrals before we move on. We still have 20 minutes. Okay, some things about double integrals that I think are somewhat obvious, but we should just make sure that, you know, we're being told we can do it. This goes back to, again, Cal 2. Remember in Cal 2 that if you wanted to do an integral from A to B, right? If you wanted to do this integral, that you were completely free to just split it somewhere at C and then break this up into two things, right? Make this be the integral from A to C and then plus the integral from C to B, right? So you can split it up into two different areas and then find the total area. This is saying, yeah, just like we split this domain into two different intervals and we can just do them separately, this says if we have a region on the ground D, we can split it into two different regions, D1, D2, and then the original double integral over the entire domain should just be the sum of the double integrals over each of the D1 and D2 respectively. So that, I think, works naturally with what we learned in Cal 2, right? All right. This one right here is extremely important. It's simple, but it's extremely important. So what we've been learning is this idea right here, right? That the double integral over D of some surface f of x, y with respect to area is just the volume, right? The volume from f down to the ground, right? Well, what if I tell you that that function f of x, y, what if I tell you it's the constant 1 function? What does the constant 1 function look like here? What does the surface f of x, y equals 1 look like? It's just up 1 in a plane, right? Up 1 in a plane. So now imagine that I had that plane that's up 1 unit, right? That's just shifted up 1 unit. And let's say on the ground, I have this thing D, right? On the ground. So I've got this plane. On the ground, I've got D. If I calculate this, right? If I calculate this double integral of that constant 1 function over D, do you agree that that's just the area of D? Area, not volume, area. So when I project this up into this plane, I get this thing up here, don't I? That's D plugged in up there. And I've got this solid shape. But how tall is it? 1. Okay, so what's the volume of this? It would be whatever this area is, right? The area of D, I'm going to call it area of D. The area of D times 1 would be the volume, wouldn't it? As long as that is 1, then it should be whatever that area is times the depth. But that's what we're saying. The volume is equal to the area numerically. Numerically, it's the same answer. So if you get an answer of 2 here, that means the area on the ground is 2. This is a unique property of double integrals, but it only works when your surface function is 1. Now, I know you're sitting there going, like, okay, so what, you know? Like, why, you know, where is this useful? It's going to become extremely useful later, okay? I'm debating right now whether or not we should go after what I want to go after. I'm not going to yet. It's better in the next section. So just for now, remember this. That double integral over D of some function with respect to area gives you the volume underneath f, but if that f is 1, then it winds up that that volume is equal numerically to the area of this surface on the ground, okay, that they're the same. All right, and then we have homework. Oh, we have this one. I must have thrown this in. This problem is just like the one we just did that I walked out of the room on. It's actually a little easier. Trying to find the volume between that paraboloid and these planes. Okay, so the difference, the big difference in this one that makes it easier is that this is your f of x, y. Like you already know what your surface is. You don't have to like solve for z like we did in that plane before. All you got to do is wrap your head around the domain. I'm not going to do this whole problem. I just want to set up the domain. X equals 0. Right? That's x is 0. Okay, y equals 1. Okay, y equals x. And finally, z equals 0. Okay, well, z equals 0 is the ground, isn't it? The ground. So there it is. There's your D. I could do that as a type 1 or type 2. Or type 2, setting it up. Let's do type 1. What are my bounds on x? 0 to where they hit each other. Is it obvious where they hit each other? 1, right, at 1. Okay, so 0 to 1. Okay, now what about my restrictions on my y between here and here? X and 1. And what am I integrating? The x squared plus 3y squared d y d x. There we go. That's the setup for that one. I hope that's a little smoother now that we did that other one. Other questions?
If we want to make it type 2.
Type 2. What if we wanted type 2? What would it be? 0 to 1. No, it's always going to be your restrictions on y first, 0 to 1, right? But now you got to go this way for your restrictions on x. So from what? 0 to here, to this. So you have to take this equation and solve it for x. So y. And then it's the same thing in here, dx, dy. Type 1, type 2. You get the same answer either way. Even though these limits of integration look different, it still will give you the same answer. All right. All right, that's the problem worked out. So this was out of the book. So this is the solution. Here it is right here. They did type 1, and they work it out, and they get 5/6. All right, I know we got a little bit more time, so please hang in there. I want to at least start the next section because it's still type 2. Still double integrals. No, 12.3. All right, so we're going to get into double integrals in polar coordinates. So look, what we've done so far is very useful for a lot of different regions on the ground you could think of, right? Like if we've got a rectangle on the ground that we want to integrate over, we're in business. We love this. This is the best case scenario, right? A rectangle on the ground, both our limits of integration are between constants, and then we can even reverse the order and it doesn't even matter, right? Here, type 1, well, that forces us to do it in a certain order. Type 2 forces us to do it in a certain order. But you can imagine all the different shapes you could get with this and all the different shapes you could get with that. As good as that is, that's still not good enough for the different types of shapes you could see on the ground. For example, a circle. A circle is not a type 1 or type 2, right? I mean, unless you could do a circle as a type 1, but you'd have to have like a function on top that draws the top half and the function on the bottom that draws the bottom half. And that could be done, but it would be a little complicated. So in order to deal with things that are not shaped like this, we have to switch our entire coordinate system over to a different coordinate system. And it makes it easier for us to deal with certain things. So how many of you have seen polar coordinates? A little bit, a couple. So some have, some haven't, a little. All right, so this first thing is just to get you to understand that, look, this has really nothing to do with calculus. This just has to do with the way we look at a flat sheet of paper. The way we've been taught is that if you want to get to a point in space, I have to provide an x and a y coordinate, right? And those numbers represent two different things. The first, the x coordinate, is how you always start at the origin, right? And this is representative of how far you go out horizontally, right? From there, you walk out horizontally that distance. If it's negative, you'll go to the left, right? If it's positive, you go to the right. And then to get to the point, you then have to go up, by y, right? But that's a vertical displacement. So this is your like x displacement, and this is your y displacement, your horizontal and vertical displacement. That's how we navigate around the plane, right? This way of thinking is called the Cartesian coordinate system. This is called Cartesian coordinates. Cartesian coordinate system. All right? That is not the only way you could have told someone to get to a point. Another way you could have done it is to imagine that you're a person standing here, okay? And let's say your eyes are pointed out the x-axis, all right? So I'm standing here, that's the top of my head, and I'm looking this way, right? Another way to get to that point, instead of telling me how far to walk out and then how far to walk up, you could just tell me, I'm pointing my eyes this way, you could tell me an angle to turn, and then you could tell me how far to walk out, and I would still be able to get to that point, right? So if you give me an angle, theta, and you give me a distance to walk, I'll call it r for radius, then that is two pieces of information, right? It's still two pieces of information that I have to give you to get to that point. Just like with the x and y, I had to provide you two pieces of information to get to that point, the x and the y. Well, in this system, I provide you the radius, which is the distance to walk, and I provide you the angle, which is the angle you turn. And you can still get to any point in space, right, on a sheet of paper. This is known as polar coordinates, the polar coordinate system. And those are our two typical systems that we use in two-dimensional space. So once you draw this picture, there are a bunch of connections between Cartesian and polar. So this is basically me doing that same idea, right? I can go to any point in space, right? All it does is change the radius, change the angle, I can get anywhere, right? And if you increase the angle past 90 degrees, and you can get to any other quadrant, right? And I could walk out as far as you need me to walk out. So it's important to understand that this ordered pair in Cartesian, so if I write, let's say I write 2, 3, and I say that this is in Cartesian, or if I write 2, 3, but I tell you this is in polar, these do not represent the same thing, right? In Cartesian, this means go out 2, go up 3. What does this mean in polar? Walk 2, but this is your angle. And so the angle would be 3 radians. So I'd turn by 3 radians, I'd walk out 2 units. That's not going to get me to the same place as this. So what is the connection? Well, we have a bunch of trig stuff from pre-cal, right? If you draw this, if this is x and this is y and this is r and that's theta, we have all these relationships, right? We know that sine of theta is opposite over hypotenuse. And then if I multiply both sides by r, whoa, I don't know what happened with that s there. Then y is r sine theta. And then similarly, x is r cosine theta. So you have those relationships, right? So I put that right here. We have x is r cosine theta, y is r sine theta, right? We also have this relationship, x squared plus y squared equals r squared. Where does that come from? Let me bring this back here. Yeah, x squared plus y squared equals r squared. Right triangle Pythagorean. So we have that as well, right? And then this last one. this relationship right here. Theta is always the inverse tangent of y over x. That just, again, comes from the right triangle. If I want to know what theta is and I know what y and x are, I just take the inverse tangent, right? Tangent is this, so inverse tangent would be theta. Okay, so those are all what we call the Cartesian and polar coordinate relationships. So now if somebody gives you a point, right? Let's say, I want to do an example before we go. Let's say that I have the point 4, 5. Let's just start simple. I tell you that this is in Cartesian, right? And I want it in polar. What's that point in polar? Well, I use my relationships, right? I know what x is 4, right? I know what y is 5. So I can figure out first from the Pythagorean, right? X squared plus y squared must be r squared, which means that 4 squared plus 5 squared must equal r squared. So root what? 40? 41. Root 41 is r. So now I know how far to walk out, right? I just need now I just need the angle. And so to get the angle, I do inverse tangent of 5 over 4. And if you do that on your calculator, anybody have it? I'm going to make sure. Do you want your answer? Let's do the answer in degrees because most of us understand degrees more than radians. I'm going to make sure I'm in the degree mode, which I am. And I'm going to do inverse tangent of 5 over 4. And I get, I get 51.3. 51.3, I'm rounding degrees. All right, we have to check, does that answer make sense or not? Does that answer make sense? Where's that point in Cartesian? To the right 4, up 5? I'm right here. Does it make sense that I should rotate by 51.3 degrees and walk out? Yes. Okay, so we got the right answer. So what is this in polar? In polar, it is root 41, 51.3 degrees. All right, now be extremely careful because if I change this problem and I make it -4, -5, I'm now here instead, aren't I? So now this is -4, -5. Does that change my r? No, because I still square them both, and that doesn't change r. So r is still the same. When you go to your calculator and you do inverse tangent of -5 over -4, do you see your calculator does not know that you basically are giving it the same input, aren't you? Two negatives together is still positive. And this is a problem with the inverse tangent. It has domain restrictions. You can't, the inverse tangent is only defined if your angle is between -π/2 and π/2. So it's still going to return 51 degrees, but it's wrong because it thinks you're here, doesn't it? It thinks it's 51.3. So how do we get the right answer? We add 180 to it. So we'd have to take that and add 180. So 180 plus the 51.3. Okay. Damn it, I only have 30 seconds. Shit. I'm going to just show it to you. I'm just going to show it to you, and then we're going to go. And I'll pick up with this next class. Here's what makes it so great, all right? The idea of polar. If I wanted to define this region right here, let's say this is a diagonal line right here. If I wanted to define this region right there, let's say that's 2 and that's 3. So what it is like part of a circle. I'm telling you right now this is 45 degrees. Okay, so it's like part of a circle that has a radius of 2, but it only goes from here to here, and then another circle radius of 3. I'm talking about if that's our region D, and we want to do a double integral over that, right? That's not a type 1 or type 2. You don't want to mess with type 1 or type 2. But if you try and describe what D is to me as a set of points, right? Set of points. But in polar, not in Cartesian. In polar. So some r and some theta, what can you tell me about all the points in this region in terms of the theta? If you're in here, what's your theta between? 45 and 90. So my theta, I'm not going to use degrees. I'm going to say between pi over 4 and pi over 2. And then what about your radius, how far you walk out? If your point's in here, you only walk out between where and where? 2 and 3. And do you see that how easy it is to define that region in polar because your theta and your radius are between two constants? So this is the equivalent of a rectangle in Cartesian. Remember in Cartesian, if we had the rectangle situation, a is between two constants. X is between a and b, y is between c and d. In Cartesian, that's what it looks like. This is a Cartesian rectangle. This is a polar rectangle. All right, so that's where we're headed. We're going to say, okay, what if we're trying to find the volume underneath the surface, but the ground is something that's better suited for polar. All right? That's where we're headed. Try and get caught up on all your homework we're up through 12.2 now, right? This is 12.3. So try, and then you have 4 problems for your take home, which is due, so that's not next week, right? The following. And I believe that only goes up through what?
11.
Yeah, so this stuff is old stuff now to us. We're already in chapter 12. So I would knock that out because more stuff's coming with chapter 12. All right, thanks for hanging out for an extra minute. You'll have a great day. If anybody needs their exam,